students, today let us learn about a new subject, that is heat transfer. Before entering to the subject, let us now see what is actually heat transfer and what is the difference between heat transfer and thermodynamics. Why I said thermodynamics? So thermodynamics also deals with heat, where work done is being done. That means when you give an input to the system, there will be an equal output of the system. So that means you have your work done. So you are taking the stage 1 and stage 2 and finally writing our work down. Only you are considering the stage 1 and stage 2 heat only. Now in this heat transfer, we will also see the heat transfer from one region to the other region, but you will consider the intervals happening between the one state of region to the other state of region with intervals of time. So that is the main difference between your heat transfer and your thermodynamics. So let us now see what actually the agenda of our this particular concepts. So let us see the introduction of heat transfer, what actually heat is, and then how actually the heat transfers in this particular region. So it takes some modes of heat transfer. So what are the modes of heat transfer, and then let us learn the mechanisms of heat transfer. So finally we will be in a position to learn what actually heat transfer and thermodynamics relation, and as well as the mechanisms of heat transfer. So, I already told you the thermodynamics definition, though it is a study of heat and work transfer, so that you will deal only with one region to the other region. Finally, we will write only the work down without intervals of time. So, in case of heat transfer, it is also a study of heat flows, but every activity involves in this particular heat transfer. So, that is why we will separately study this subject, heat transfer. So in this heat transfer, now let us see what are the applications of heat transfer. So we have many applications of heat transfer in this particular engineering sector, where it deals with cryogenic, it deals with chemical, it deals with aerospace, automobile, mechanical engineering. Everywhere we will use this particular heat transfer. So before going to your heat transfer, I already told you what actually the main three processes that we will use in this heat transfer. That is your conduction, convection and radiation. So let us see what actually conduction is, what actually convection is, what actually radiation is in detail. So I already told you conduction. So conduction deals with the particle heat transfer. So every solid particles what we are having, every solid has some particles. So if a particle is having less space in between, that is said to be as your solid. If it is having more space, that is said to be as liquid, and if it is having a larger space between the particles, then you will say it as a gaseous. So in this all the three modes we have our heat transfer. So transferring from one particle to the other particle of heat, then you will say that condition, that type of heat transfer as your conduction. So I already told you the modes of heat transfer. So we have one mechanism. So the conduction mechanism equation is given by Fourier. So this Fourier law is given by the Fourier law of heat conduction equation. So let us now first study the Fourier law of heat conduction equation. I already told you heat will flow from one region to the another region. The other region having higher temperature and the one region having the lower temperature. So this is the heat is directly proportional to the temperature difference, that is sum T2 minus T1. If we remove the proportionality sign, this happens with respect to your time intervals. So if we remove the proportionality sign, so Q will be equal to sum T2 minus T1 by small t. So this is happening where in a unit area. So we have to have some proportionality constant. So that constant is called as your small k. So small k is given as your thermal conductivity, which is denoted by small k, and the units are joule per meter Kelvin. So here the temperature T2 is greater than T1. Actually we'll write this equation as Q is equals to minus Ka dt by dx. So in a small interval of time. So what is this minus here indicates? It indicates some negativity. So we will write this minus to make this temperature difference positive. So this temperature difference, how we will write? T1 minus T2. So to make this positive, that's why we are writing here as T1 T2 minus T1. Here our condition is T2 is greater than T1. So finally our equation is becoming as Q is equals to Ka dt by dx, where Q by A is equals to K into dt by dx, where this Q by A is called as heat flux, where Q by A, the heat per unit area, is defined as heat flux. This whole concept comes under your Fourier's law of heat conduction. This K always differs from the material to material. So you have to have thermal conductivity. We have different thermal conductivities. We have different thermal conductivities for air, for wood, etc. We have so many thermal conductivities like that. So now let us see the introduction of your convection. So as we all know that more dense will have cooler regions, less dense will have warmer regions. So obviously there will be some convection current that happens either from lower to more or more to lower. So that type of condition is called as your convection. Again, this convection is divided into two types. I already told you, with phase change and without phase change. With phase change, we have your boiling and condensation. We have seen in the last slides. Now we will see the main convection that is being divided. So that is your forced convection and natural convection or free convection. So here the name itself indicates what is forced convection. So if you consider an object and you are forcing some air on it or some amount of fan or something over it, so then there will be change of temperatures between that particular object and the surroundings. So if that surroundings and that object happening, then we will call that as your forced convection. If that object is kept in an atmospheric air, so due to those density difference, there will be some heat transfer that happens between the object and the surroundings. So that you will tell you as a natural convection. So you can see an example over here of a boiled egg or a hot egg. So it is clear the air is on this and we are forcing some fan air to the hot egg. So there is some amount of heat transfer between the hot egg and the surroundings, and as well as natural convection where the hot egg is kept in the air. So that air, due to those density differences, there will be the heat transfer that is happening. So now let us next see the another mode of transfer, that is radiation. Before going to your radiation, let us give a small example of sun and earth. We all know that sun and earth is of some distance, but we have some waves coming out from sun to the earth. What are those waves? Let us say those waves are infrared waves. So it requires some amount of energy. So there will be that energy is called as electromagnetic waves. So it doesn't require any medium to transfer that type of mode of heat transfer, that we'll say that as your radiation. So unlike radiation, we have your equation, that is your Stephen-Boltzmann law. In this Stephen-Boltzmann law, we can say that as the emissive power is directly proportional to the fourth power of temperature difference, fourth power of temperature difference. If we remove the proportionality sign, E will be equals to some area, unit area into delta T power 4. So we have to introduce some proportionality sign, so that is your sigma A into delta T power 4, where sigma is called as a Stephen-Boltzmann constant and it is being given a value 5.67 into 10 power minus 8 watt per meter square Kelvin per 4. Apart from this Stephen-Boltzmann law, we have our convection natural convection equation, that is your natural convection equation. So this equation is given by law of cooling. So this Q is directly proportional to your temperature difference from surface. This is your surface, object surface, and this is your surroundings. So here they said that there is some temperature difference. If we remove the proportionality sign, so in an unit area, surface difference minus surroundings, so we have to introduce your proportionality sign. This H is called as your law of convection heat transfer coefficient. So this equation you have to remember for your law of convection, and this equation you have to remember for your radiation equation, and Q is equals to K minus Ka dt by dx for your conduction equation. So these are the modes of heat transfer that is happening in our heat transfer subject. So we have to know these modes of heat transfer, and then in the next class we will deeply go into your conduction equation, where we will study what actually conduction equation is, how we are deriving our conduction equations. So we'll continue in the next class. Thank you all.